This is the second section of the sequences and series chapter, and this is arithmetic series. Now the only difference between an arithmetic sequence and a series, well, if this is a sequence, and I think I used this sequence in the last video, so this one's going up in sixes, okay, whoops, so this is a sequence here, separated by commas. If I find the sum of the numbers in a sequence, it now becomes what we call a series. So as it says up here, an arithmetic series is the sum of the terms in an arithmetic sequence. So the top one is a sequence, this is a series. That's just the sum of the terms in a sequence, even if the terms in that sequence, let's say something like this, even if they're negative, we would still add them together. So that'd be negative 32. So that's a sequence, and the series would be negative 12 plus negative 12, or negative 2 plus negative 12 plus negative 22 plus negative 32. Yeah, so it's still a series. You're still finding the sum, even if those numbers are negative. You still add them together. Now, many years ago, it's a story that said that there was a young boy in a class. He's probably like primary school age or just started secondary school, and the teacher thought he'd be clever, and he would ask this young boy, his name was Gauss, ask him a question, and he basically said, what I want you to do, and he thought this would probably keep the kids busy for a long while, is add together the numbers 1 to 100. And he probably thought, well, you know, I can sit back, have my cup of tea, whatever it is they drank in those days, and you know, this will keep them busy for ages. Well, after a couple of minutes, Gauss stood up and said, I've got the answer. And the teacher can believe it. This is before the days of calculators, so he wanted them to do this: 1 plus 2 plus 3 plus 4. All the way up to 100. Now he came up with an answer very quickly, and he said it's 5050. And a teacher was amazed. I think, how did you manage to add that together so quickly? And this is actually a series, isn't it? The sequence 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 100, and we're finding the sum of that. And he had a really ingenious method. What he did was saying, okay, let me think of, let's try with an easier one. Let's add together the numbers 1 to 10. So let's say we want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, let's say I want to work out what those numbers add up to. Well, what he did with the numbers 1 to 100, I don't think he wrote them all out, was say, okay, let's do the same sequence but backwards. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now, if you add together each column, each pair of numbers, you'll notice something. So I'm adding together each of these columns here, and what you'll notice is they all add to 11. So 11, 11. So each column adds to 11. Now, how many lots of 11 have I got? That should be easy to work out. I've got 10 sets of numbers. So the sum of that is 10 times 11, which is 110. But what I've done, I've actually added the sequence that I've wanted in black. I've done it twice because I wrote it out again underneath. So this is the sum of two sequences that go from 1 to 10. So if I divide that by 2, I actually get the sum of those numbers which I wanted. So the numbers 1 to 10 add up to 55. Now if you extend that to the numbers 1 to 100, you don't need to write all 100 numbers out. You can just write a few out and see the pattern. So if I've got 1 plus 2 plus 3 dot 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 all the way up to 100, what would it look like if I wrote the numbers out, or that list out backwards? So 100, 99, 98, then this would be 2 and then 1. You can see that what you have is these 101. Each column adds up to 101. Now I don't need to write them all out because I know that I'm going to have 100 101s. So 100 times 101. That will give me 101, so 10,100. Divide that by 2 because I've got two lists going up to 1 to 100, and I get 5,050. Now look how quick that is. And I can imagine in Gauss's class all the other pupils were sitting there like doing 1 plus 2 and then adding 3 and then adding 4, and probably only got up to about 11 or 12 before he got the answer. Now sometimes this method of finding the sum of arithmetic series is called the Gaussian method, because he was the one that came up with this, and lots of other mathematical stuff as well. So it's worth looking into, worth finding out a bit about him. Right, example 4. Well, I think we've just done that, haven't we? Proved that the sum of the first 100 natural numbers is 5,050. Well, natural numbers, that just means the counting numbers. Yeah, the counting numbers are natural numbers. Now, just like we use the letter R for real numbers, we use this N for natural numbers. Yeah, so our natural numbers are the counting numbers, so 1, 2, 3, 4, and so on up to N. So if we want to prove that the sum of the first 100 natural numbers is 5,050, I'll just run through that proof that we did very quickly. So you would write this out. So actually what you could say is this is the sum of, and we can write it like that, of the 100 numbers. This is also going to be the sum of the 100 numbers, but now written out backwards. If I add those together, I'm going to get two lots of the sum of those 100 numbers. So 101 plus 101 plus 101. It's gone slightly out in column wise. 101 plus 101. So 2 times the sum of these 100 numbers is going to be 100 times 101, which is 10,100. So the sum of those 100 numbers is going to be half of that, half of 10,100, which gives us the 5,050. You can pretty much do that without any type of calculating device. So there's our proof. Now, we do have a formula that allows us to find the sum of an arithmetic series, and that's this, and we do need to be able to prove it. Now it's very similar to the proof for 100 numbers, but we're going to be using A and N and D. So let's say I want to find the sum of the first n numbers? Well, that's going to be a sequence where the first number is a plus, the second number is going to be a plus d. Yeah, so a is the first one, a plus d, so a plus one common difference. The third term, a plus two differences. Third term, a plus three differences. Now I'm going to do dot dot dot, go all the way to the end, and then I'm going to have a plus n minus two differences, and then if I go up to the nth term, that's going to be a plus n minus one differences. Yeah, so that's the terms of a sequence written out using a, n and d. Now, just like we did with the numbers 1 to 100, we're going to write it out backwards. So underneath a, we're going to have a plus n minus 1d. Underneath the a plus d, so I'll just put an arrow down like that. Here we're going to have a plus n minus 2d plus, and then underneath this one we'll have a plus n minus 3d plus dot dot dot, and then when we get to here, this is going to be a plus d under that, and under that one it's going to be a. So all we've done is written the sequence out backwards, or the series out backwards. So what happens when we add each column? Well, first of all, we're going to have two lots of the sum of these n numbers, and probably we know that each column is going to give you the same total, but the easiest ones to probably see what it's going to be is looking at the first one and the last one, and that will give you 2a plus n minus 1d. Now I know this has got like n minus 2 and n minus 3, but when you add a d to it, then this becomes n minus 1. The same here, this will become n minus 1, same here. So what we'll have is 2a plus n minus 1d. That's what every column will be. Now, how many times have I done that? How many pairs am I adding up? Well, n pairs, because I've gone up to n numbers, so we need to times that by n. And then the last thing we need to do, because we've got two lots of that, we're going to divide it by 2. So now we get the sum of n numbers is n over 2, and then in brackets 2a plus n minus 1d. So this little expression here, we can find the sum of any series using that, using the common difference, the first term, and n number of terms. So you do need to remember that proof, because you want to be able to replicate that in the exam. So we're going to use that formula, so we'll just write it down here, that the sum is equal to n over 2 2a plus n minus 1d. So find the first 50 terms of that series. So a is 32, because that's the first term. D is, I can see it's going down by 5, so D is negative 5, and n is 50, so you just substitute that into the formula. So the sum of these 50 terms is 50 over 2 times by 2 times 32 minus 50 minus 1, n is 50, times by d, which is negative 5. So we'll stick that on our calculator and see what we get. So 50 over 2 is 25, so I can do 25 times by 2 times 32 is 64. Oops, plus, I'm not sure why I put a minus there, plus basically 49 times by negative 5, and I get negative 4525, so negative 4525, negative 4525, so that's that one. Now when you see a question that says find the least number or the greatest number, first thing you need to be thinking to yourself, well, this is some sort of inequality that I need to solve. I can see here this is the sequence and I want it to exceed 2000 here. So let's write down first of all the formula, and then we'll think about what it is that we know and what we don't know. So the first term is A, which is 4. I can see it's going up in 5, so D is 5. I don't know N. N is what I need to find on this question. But I do know that I want this sum of however many terms it is to exceed greater than 2000. So let's put that information into the formula and see what we get. So I want this sum of n over 2 times by 2a, so that's 2 times 4, plus n minus 1d, n minus 1 times by d, and d is 5. I want that to exceed 2000. So the rest is about trying to solve that to work out what n must be greater than, and then from that we can work out n. So n, let's times both sides by 2 first. So we've got 8 plus, and I'm also going to expand the brackets here, so I'll get 5n minus 5. So that's greater than 4000. Let's expand the brackets. Now I've got n times 5n, so that's 5n squared. Looks like it might be a quadratic. 8 minus 5 is 3, so times that by n, so we end up with 3n. And I'm going to take the 4000 across. So I've now got that quadratic that I need to solve. I don't really want to sit down and try and work out all the factors of 4000 to try and solve it. So I can use my calculator or use the quadratic equation to solve that, which I think I will do. A is 5, B is 3, C is negative 4000. So using the quadratic formula, I have minus b plus or minus square root b squared minus 4 times a times c all over 2a. Now I'm guessing I'm going to get two solutions for n, and I will ignore the negative one because n can't be negative. So let's work that out on our calculator and see what we get for that one. So the two solutions I get 27.985, and the other solution I get for n is negative 28.585. Right, so we ignore the negative solution because n can't be negative, and also n must be a whole number. Now what we've actually worked out here is that n must be greater than, because what we found there's a critical value, 27.985. So that means that n, the first whole number it can be, is 28. Yeah, so that's the least number of terms you need for that sum to exceed 2000. So you can always check. We could type in using the sum of n, and we could work out what that's going to be. So I'm going to do a little check over here. Again, you know, you don't need to do this. So my little check here, I'm going to work out, well, what is the sum of 28? And that's going to be 28 over 2, and then 2 times a plus n minus 1, so that's going to be 28 minus 1 times by d, which is 5. Let's see what that gives us. So just typing that in now. So 8 and 27 times by 5. So I get 2002. Now, if we don't need to work out S27 because we know that this sequence goes up in 5s. So the one before that would have been 1997. So yeah, we know that's right. Yeah, we know we've got the right answer by checking it, and that's useful to do when you've got the time. Right, you should now be able to do exercise 3B on pages 64 to 66 of the Pure 2 textbook.